Welcome to my talk, presenting working on Gaussian plane wave neural operator for electron density estimation. I focused on delivering the insight of our work shortly, but I am open to discussing the paper or related works. Let me start with a short summary. We propose a new model for estimating electron density using physics and chemistry concepts like Gaussian type orbiter and plane wave basis. Our framework is a neural operator that learns the mapping between the functions, ensuring SE3 equivariance and periodic boundary conditions. We also verify the effectiveness of our hypothesis by experiments. The electron density is the probability of finding electrons in a specific area. According to quantum mechanics, the electron position should be represented by the probability over the space. And we can use the electron density to predict the material's atomic properties. From density functional theory, the properties of a molecular system can be determined by the functional depends on the electron density. From DFT, we can use it to any domain that related to predict the atomic properties in principle, like battery cathode design, drug design, or solar cell materials design. Our main task, electron density estimation, is learning the mapping between the molecules to the electron density function. This task can be regarded as the sparse function to continuous function mapping, so we named our work as neural operator. This is our method overview. We make parallel predictions, GTO-based for local regions and PW-based for global regions. GTO-based prediction utilizes the coefficient learning of the GTO basis, and PW-based prediction utilizes the lattice-based discretization via the proof nodes. Finally, the output is evaluated at arbitrary query points by summing up two prediction layers. So, why do we have to use two types of bases, GTO and PW? Our answer is to integrate the advantage of each basis. So, we decompose the electron estimation into two regions, that is, regions near the atoms and far from the atoms. This decomposing makes representation to focus the region where they are suitable. Namely, short range is influenced by the GTO and long range is influenced by the PW. Let's see the method in detail. The GTO-based prediction is constructed by the linear combination of GTO bases. Our model predicts the coefficients of spherical harmonics and radial bases by TFM-based network and message passing. The PW-based prediction is started with placing the proof nodes that discretize the lattice uniformly. And we aggregate the message from atoms to proof nodes to initialize the proof features. And we iteratively update the proof features by a convolution operator using the PW basis. At the final layer, for given a query point, we compute the output by message aggregation from proof nodes to query points. Let's see our result. Our model outperformed 10 baselines in the periodic materials like QM9 or MD. Also, our model excels with the smallest number of parameters in QM9. And our model outperforms the baselines regardless of the lattice type in the crystalline materials like materials project dataset. Thank you for watching. More details like ablation and time complexity analysis are in our paper and GitHub. and I'm open to talk and discuss and hope to meet you in Vienna.